I'm Wolf McNally. I'm the lead researcher of Blockchain Commons, and in this talk, I'm going to discuss GSTP, which stands for Gordian Sealed Transaction Protocol. This is a protocol for transaction among various kinds of peer-to-peer and client-server devices, and we'll explain the motivations for more as we go. But first, I also want to thank our research sponsor, which is Foundation Devices, and I think we have Ken Carpenter here today from Foundation Devices. This GSTP we started developing with it, showed it to Foundation, and Foundation said, oh, we might be able to use something. And so they have generously provided funds to enable us to extend this, and the benefits of that are now available to the entire community. So we definitely thank Foundation for sponsoring us in this regard. So I want to discuss briefly our Rust stack. Everything you see here on the right is available on crates.io. The ellipses are libraries or crates, and everything here is a crate, but the ellipses are libraries, and the rectangles are actually command line tools. So in the previous part of this talk, we discussed both the seed tool CLI and BC envelope CLI. Christopher a moment ago mentioned the depot server, which is a way that people can anonymously and securely store small pieces of information. Could be large, but often small, which are shards of keys, which cannot be keys cannot be reconstructed from them individually, but it's a way of social key recovery. And then these things build on these other crates we have. We also have the DCBOR CLI, which is a deterministic CBOR CLI tool that we have. And so I just want to point out a couple things here that, there are transitive dependencies here that we haven't shown, like SSKR, and pretty much everything else depends on BC RAND for fuzz testing and things like that. So we've simplified the diagram by eliminating the transitive dependencies. I also want to point out that we ourselves benefit from the open source community. For example, our BC UR crate adds DCBOR functionality to the UR crate by Dominic Spiker. And so he actually took our spec for UR and our other reference implementations, implemented a new third-party crate. And I said, well, this is great. We don't have to implement our own now, but we do want to add some direct DCBOR capabilities. So we actually created our BC UR crate based on that. And that's what the rest of our stack is based on. But, we definitely thank Dominic for his implementation, as well as other third parties who implemented our UR standard as well. So we're also going to focus on this particular crate, the BC envelope crate. This is where our direct support for GSTP is currently located. The BC envelope crate, if you look at the cargo.toml file, in it has quite a few different features. You can basically use it as is, where all the features are turned on by default, and that's fine. And Rust is very good about, in a large code base, compiling, stripping dead code and not including what you don't need in your final thing. But if you want to actually turn off any of these features for specific purposes, you can turn off GSTP, you can turn off encryption, you can turn off whatever you don't want, because envelope itself is currently an internet draft with the IETF, and it's very spare. It's only got one thing that I would call a feature, other than its general architecture, its hierarchical kind of Merkle tree-like structure. One feature that's kind of inherent to it, which is elision. But all these other things that we're going to be talking about, including encryption, compressions available, although that's not relevant to today's talk, all these other things are features that are layered on top of that. And we have other blockchain commons research or BCR documents that describe each of those features. Those are all implemented in this crate and turned on by default. So you can use those just by, the batteries are included here. So I want to talk about, kind of an overview or motivations for GSTP before we get down into the details. Obviously, if we're describing a peer-to-peer architecture, I just want to acquaint you with make sure we're on the same page regarding certain terminology. We're going to talk about requests and responses, where a request is created by a sender and received by a recipient, and where the response, the roles are reversed of sender and recipient in the response. Fairly straightforward. Where it starts to get interesting is that GSTP is very agnostic about the channel you're using. So that channel could be the internet using REST or some, TCP/IP, UDP, whatever. It could be Bluetooth, which has various kinds of security built into it, but also you can use it with no security at all. It could be NFC, either NFC cards or other tools that relay data using NFC. Could be Tor, which is obviously very secure, but again, it's like an extension of the web. Or it could be even something like QR codes, which have absolutely no security at all, Our stack actually includes a way of including arbitrary amounts of data in QR codes using multi-part URs. And that's, the subject of other talks we've done and so on. So, but it'd be nice if you had a protocol that could be equally secure with all these because, oops, let me do that again. Because the one thing you can say is that because these are all consistent, you have to assume everything is unreliable and insecure from the start. And you'd like something that kind of handles all these cases, which is why we designed GSTP, Gordian Sealed Transaction Protocol. So I want to talk a little bit about the kind of the goals and key components of GSTP. The first is that we want to support asynchronous communications between peers in peer-to-peer environments where there could be multiple peers chatting back and forth, as well as client-server environments. We want to support multimodal transactions, and this means using more than one channel as desired. So you might start with a QR code and then continue with Internet Protocol or Bluetooth or anything like that. We want to support out-of-the-box unique IDs for request response pairs. This is useful for auditing, for making sure that for matching requests and responses across time and space. We want to support bidirectional encryption using public key cryptography, including encrypted multicast. So if you're actually chatting in a multi-way, we want to have multiple receivers. We want to have self-signed requests that include public keys for authentication. And this supports things like trust on first use or TOFU, but also enables you to, immediately see that the person who sent you the message is also the person who owns the private key that signed the message. And this is like a standard feature of GSTP. We very critically, Christopher mentioned this earlier, we want to support message encapsulated state. And this is including having a standard slot for what's called a self-encrypted continuation. And this is a black box to the receiver that they are obligated to send it back to you so you can continue the computation once you receive their response. And that's also bidirectional. Both, all senders and receivers have the capability of including self-encrypted continuations. And then we also, in this continuation mechanism, we implemented expected response ID and continuation timeout mechanisms to avoid things like replay attacks. So that's also very useful. And generally speaking, I've always been a huge fan of idempotent actions, which are actions which, if repeated, cause no additional effect. So our architecture for envelope, for GSTP and things like that are designed to, while we don't require it, we certainly encourage the design of APIs and architectures that rely on idempotent actions. What are the benefits of this? Well, we want to reduce state management. We want to, our continuations allow peers to offload private state information into the past messages, minimizing and ideally eliminating the amount of local state needed for ongoing tasks. And this hopefully, when combined with idempotency, increases fault tolerance. We want to make this more scalable. So especially like in client server situations, it's not always the case where adding more servers gives you more bandwidth because if they all depend on a set of shared state in a database, then there's database contention and so on. Whereas if all the state you need to continue the computation is included in the request that you can access because you encrypted it to yourself in a previous step, any server can handle the request. And so that allows what's called horizontal scalability, which is, adding more servers gives you linear increases in capacity. And obviously security, self-encrypted continuations, maintain the privacy and integrity of the sender's state information. And then we include the expected response IDs and timeouts and continuations to help prevent manipulation of continuations for like replay attacks. And efficiency obviously is a big concern as well. So envelope is a binary structure. And it's designed to be, deterministic and minimalistic. So you only need to pay for what you use. So continuations and responses enable things like pagination, streaming, and incremental processing of large result sets. Obviously, you know that if you have used certain REST APIs, you might get back a token from the server, which basically says if you want to continue this pagination of this, send back this token. Same idea here, but actually much more flexible and very secure. So to lay the foundation for this, I want to discuss requests and responses as distributed function calls. And remote procedure calls are nothing new, but I want to make clear how we've implemented them using our stack and how it fulfills the goals that we've just discussed. So I'm going to start by looking at just a Rust kind of a generic function signature here. It's an asynchronous function, which means it can be paused and handed off to other threads while it happens. It just has a generic name do it. It has two different arguments of two different types. The ellipsis indicates it could have more. And then it has a result which in Rust basically is either a success type or a failure type. And this is all highly relevant to what we're translating this to. Of course, this applies pretty much to any language. So this is how that appears as an envelope. Now, earlier in this meeting, I discussed the general structure of envelopes. Envelopes always have a subject, which in this case is the function identifier, and then a set of assertions, which are predicate object pairs, which essentially make assertions about the subject. And that translates in this case to the function identifier, and the arguments are assertions on the function identifier. These chevrons here essentially are shorthand for CBOR tags, because again, this is a human readable form of a CBOR structure. So it's important to realize that, you know, we're translating it to text. And so we could just, you know, spell out the name. This is function, and surround this with parentheses. This is parameter. But because we do this so much when we deal with what we call envelope expressions here, we have a shorthand, which is these double chevrons. And because this is a human readable format, you never need to type these. It's always for output. This is not a round tripping format. But it is essential to understand what's going on inside envelopes as you construct them and use them. And so this envelope format is widely used. But we're going to come back to envelope expressions in a minute. But this is essentially what an envelope looks like that translates this. So what do we do with this from here? So we want to encapsulate this in a request. And to do this, we generate a random ID. This is what we call an apparently random identifier, which is like a super UUID. It's actually 32 bytes, which is twice as long as a UUID. Even though we only show the first four bytes of it for brevity here. And this is a CBOR tag. This is also a CBOR tag. So it's nested CBOR tags showing this array is a request. And this is the subject of the envelope again. It had the subject has one assertion, which is the predicate body, and then this as the whole expression as the object. I'll come back to that in a moment. On the response side, it's the same basic pattern. There's the same array, the same ID, because it's the response to this. However, it's tagged response, not request. And then it has either the predicate result with the success type, or the predicate error with the failure type. So again, I'm going to kind of hammer this home a little bit here. This is the subject of these envelopes. In one case, on the left side, it's request with the array. On the right-hand side, is response with the array. And each of these envelopes has exactly one assertion on it. In the first case, it's body with the expression. In the other case, it's result with success, or error with the failure. I want to point out here that this is the predicate, which is the single quotes indicate this is a known value, which in envelope parlance is just actually it's in a small integer. So if you see things enclosed in single quotes, it's not a string, not like you'd see in a JSON file. It's actually like 2 or 3 bytes maybe from a 64-bit known address space. You can use strings as well, though. There's no reason why you can't use strings. There's no reason why you have to use known values. So again, this kind of speaks to the flexibility of envelopes. I want to point out that, because this is a common mistake people make, that on the left-hand side, that's not the object. You know, there's predicate object pairs. This is just the subject of the actual object. And so if you want to see the whole object of that assertion, it's the entire envelope expression. All right. And these are examples of complete assertions. So just a single argument assertion, or a result, or error assertion. All right, so now we're going to look at things from the sender's perspective. We have a request, which has the assertion, which is body, and the expression, which is the object of the assertion. And now we want to add the things that make Gordian sealed transaction protocol useful in what it is. The first thing we want to add is an authentication layer. We want to make sure that the receiver knows that whoever sent this owns a private key, which is essentially the key that's been signed with. So if we're going to actually provide that public key, so we add an assertion called sender public key, and we add our public key base to this. This is a Schnorr signing key. As I mentioned earlier, we support SSH keys now, but our stack currently uses Schnorr keys for everything else where you don't need SSH keys. And then we also add a sender continuation. Now, this is what we want to receive back when we actually are, because we're the sender in this case. If we want to, when we receive back the response to this, we want to continue our computation without storing state locally. we need to encapsulate that state here. And that state, again, what you're seeing here as the capital S state here, that can be any envelope. It means it can be arbitrarily complex. But we're just using an identifier for the type here. But the thing is, we're going to encrypt it. So this is now encrypted back to ourself, as indicated by the light blue, which is the sender's color here. This is encrypted to ourself, only we can read it. So we're going to send this, and the receiver is going to be obligated to send it back to us. We are also going to include the receivers, the recipient's continuation, which is what they sent to us that's encrypted back to them, as indicated by the orange color. So this has always been a black box to us. We received it maybe at some point in the past, but it's optional. If we didn't receive one, we don't attach it. But we don't know what's in here. It's only for use by the receiver. The next thing we want to do is actually want to verify the envelope by adding a signature. And as I mentioned elsewhere, because an assertion only is on the subject, and because the subject is just this string here, the request of the request ID, all that would do is verify this. We want to verify the whole envelope, however. So this isn't the right way to do this. What we're going to do, right, that's the actual subject. So we're going to remove that, and this is how we do it correctly. So we want to assign the whole envelope. And to do that, we actually want to wrap the envelope in another envelope. And this is a standard feature of envelopes. You wrap an envelope, and then now the subject of the envelope is the whole previous envelope. And now we can add its own assertions to it. So now when we add the verified by signature, then we are now, we've basically made it impossible to modify any of the contents of the subject, which is the area in curly braces, without invalidating the outer signature. All right, so now we've got a signed request. We've also included our public key base. So with nothing more than that's here, the receiver can verify that whoever is identified here must have also the corresponding private key. So that's the main thing we've done there. And this is useful for trust on first use and things like that. We'll discuss that more a little bit later. The next thing we want to add is our layer of encryption. So again, if we just like when you sign an envelope, that's an assertion that only makes an assertion about the subject. When you encrypt an envelope, you're only encrypting the subject. And so if you encrypted this right now, you'd basically have the encrypted envelope with the verified by signature. And it's important to realize that with envelopes, the signature would still verify, because even encrypted structures in envelopes, they declare their hash of the unencrypted value. So so the signature still verifies you when you transform an envelope in this way, but we want even this to be entirely hidden, because it could lead to correlation attacks that we don't want. So we're not going to encrypt that. We're actually going to do the same thing we did before. We're going to extend the subject. We're going to assign the whole envelope. We're going to wrap the envelope, and then we're going to, which basically makes that the whole subject of the envelope. We're not going to add any new assertions to it yet, but then we're going to encrypt that. And now we have a symmetrically encrypted envelope. That's it. It's all it is the envelope. Now, I said symmetrically encrypted, but we want to use public key cryptography here. So what do we do? How do we deal with this? All we do is we add one assertion, which is called a sealed message. And again, as indicated by the orange color here, this is created using the recipient's public key. It also includes an ephemeral sender. That now it's not our public key in this, but it's an ephemeral sender we create just for the sealed message, and we attach this has recipient to it. And this basically means that when the recipient receives it, they can use the ephemeral sender's public key, which is included, and their private key, use key agreement to find the actual, to create the, to recover the symmetric key that this was encrypted with. So that basically allows you to, this is called ephemeral static public key encryption, basically. So because on our side, we've just created ephemeral sender, we're using their static public key. And so we've encrypted this entire message in a public key way. And we can add more than one of these assertions too, if we want. And I mentioned encrypted multicast. This is where if you wanted several receivers to be potentially decrypt this message, you could add more has recipient assertions with sealed messages that encrypt the symmetric key just to those recipients, and then that set of recipients could also decrypt this message. All right, so this is what is actually sent to the sender. So sent to the recipient, and on the recipient side, now they're going to reverse this process. They're going to use their private key, recover the symmetric key, and decrypt the original envelope, leaving this. So now we stripped off the encryption layer, and now we have the authentication and request. So the next thing this does, and this happens automatically in our stack, is the next thing it does is it extracts the sender public key you see there, and then checks that against the verified by signature and makes sure that those match. And that's an important part of the process to avoid spoofing and things like that. But it's pretty much provided as part of the batteries included nature of our Rust stack. So once that happens, that's stripped off, and now you have the request. The next thing you can do is you have what's called a sealed request structure, and then you can parse out the various parts of that, including the ID, the sender, the peer continuation, which is the encrypted black box that you're going to pass back to the other side again, the state, which starts out encrypted, but now because you're the recipient, you can decrypt it. It's automatically decrypted for you using your private key, and now you have everything you need to actually execute the remote procedure call, to do it with the two arguments. Once you do that, then you compose your result, which is either success or failure, which is, again, before uses the response, the same ID with the response tag, and the result and success type assertion. And then we reverse the process again. We add the sender public key, our sender public key in this case, not the previous sender's public key. We add our state continuation, but we encrypt it. And again, this happens automatically in our stack. And we add the recipient continuation, which is what we're passing back to the other side for them to continue their own computation. And finally, we wrap it and verify it with our signature. And then we encrypt that and give it the has recipient sealed message so that the new receiver can decrypt it. So it's exactly the same process on both sides. So we briefly want to discuss the trust on first use, or TOFU pairing, this is what our Gordian depot uses. It assumes that there's people out there who want to back up their seeds, and they want to store a small piece of data like an SSKR share, which they need to retrieve a quorum of later to recover their highly sensitive seeds, but they don't want to trust any one party with the whole seed. And they don't necessarily want to do this as a public service. People may want to make it so you don't have to pre-register for an account. So how do we handle this? So in this case, we have a client-server architecture, and the server starts by publishing a discovery message. And the discovery message, the main thing that it needs to put in the discovery message is its public key. And this is not an encrypted message. This is essentially something that's open and discoverable if it's a standalone device. This could be published as a UR with an envelope. If it's a standalone device, it could display a QR code, which is then read by a camera. Or if it's like the depot server, for instance, it provides a single GET call, which allows you to get the public key. And then from then on, it's all post calls with just envelopes, and no third party can tell whether it's a request or a response or whatever, because it's all just UR envelopes going back and forth. Once the client has the server's public key, and I should mention that any of these channels can be mixed and matched for this. So the discovery packet can be sent one way, and then further communications can be carried on through any of the other channels that you want to support. So then the client now can compose that full stacked request that you saw with the authentication encryption layers, and then the server now has the client's public key, because that's included in the client's message, and so it can send back a response that can only be read by the client. So that's how you bootstrap a trust on first use kind of conversation using GSTP. So I want to walk through a little bit of code, and I don't want to belabor this because not everybody reads Rust in the audience. So I'm going to go kind of quickly, but I just want to kind of show how it looks in code when you strip off these layers and you process an incoming request from, say, the server's point of view. This is a function called handle request string, and this assumes that you can see here that it's receiving a UR string, and it's also returning a UR string. So this is the top level of a server that receives strings and outputs strings as its responses. And most of this is error handling code here, but the important thing here is the from UR string, which actually converts the UR, which is just text, into the binary structure, which is an envelope, by stripping off that UR. So now it has the request. And now that handles it down to the handle request method here, which receives the envelope as an encrypted request. As you can see, it's still in the encrypted state. It hands that down to another function called handle unverified response. And mostly this is here to handle errors from that. Notice that there's a function called new early failure here. It's used here as well. This is where an error occurs say, for example, in decoding the UR, maybe there was the UR was corrupted. You don't know anything about it. You don't know who sent it. You don't know what was in it. You can't tell because you can never get past that. So you have to send back a message that basically says this was an invalid request, or there's some kind of other message, error in like you couldn't decrypt it for some reason. Like it was maybe, for example, it was sent the wrong, it was encrypted to the wrong public key, so you couldn't decode it because you have the private key. You have a private key, but it wasn't the private key that was necessary. So these are causes of early failures. So then that's passed down to the handle unverified request, which then, and a lot happens here. This is the sealed request, try from the encrypted request. And this actually strips off the outer two layers and actually verifies that the signature is created by the person who actually enclosed their public key. So you know that much. You don't know that they're in your database. You don't know that whether you're doing trust block first use or not. That's for you to decide at this lower level where you're actually handling the verified request. But at this point, you can parse out all this information, the ID, the function, the sender, public key, the peer continuation, the seal, and then basically create a sealed response. And this is the next level below. So this is where we call handle verified request with the sealed request. And then this is where we generate the response. There's two ways of generating a response, either in response to the successful execution of this, or if there's a failure. Now we can pass back a fairly detailed error message where a wrong parameter was added, or the person is unknown in the database, or whatever. So this is where, so we again have the OK and error responses here. The last thing before we send back our response is that we want to add there's two last things. One is we want to add the authentication layer, and that's where we're saying we're actually creating this sealed response, which includes our public key. And then finally, we want to create the actual sealed envelope, which we're passing our private key here, so we can actually use it to create our encryption layer. And we also are adding an expiry date. So what this does is this actually puts into our own continuation the last date which our continuation can be used. So that's checked up here. So if there's one of these that arrives and the continuation has expired, you can say, sorry, it's too late to use that. That's one of the two checks. The other one that it's not shown here is expected request ID. That's because this is a response, not a request. But the client generally would put an expected response ID into that, which the server will return as part of its continuation, and that will be checked by the client as, oh, well, I was expecting this particular response ID, but your response ID is different, so I have to reject this. Okay, so one layer deeper, we actually handle a verified request where the unencrypted, completely parsable request comes in, and as you can see, this is where it's dispatched. And I just wanted to point out that there's, in this case, for example, the start recovery function. This is where a user says, oh, I lost my public key, or I want to use some other method, that a fallback method to recover my share. And in this case is a case where the server is actually saying back, okay, here's my continuation. Here's what the start recovery needs to actually do, change rotate your public key to a different public key. And then this is encrypted and handed back. And again, this is just a black box to the client, but the client has to hand it back to you at some point. And that happens here in finish recovery function. So this is where the server basically unwraps the state and basically says, oh, okay, this is what I need. And so I'm going to call, I'm going to actually finish the recovery, rotate the public key. But if that state is missing, it can't do it. So, again, the interplay is anything you need to continue. This is the start of the function. This is the continuation of the function. And the difference is this may come back through some other method, like through a phone number or through an email or something like that, something that has nothing to do with how this request was originally made. But that's the second factor that requires a user to authenticate so they can actually rotate their key. All right, sorry if that was a little bit disjointed, but that is basically the walkthrough of Gordian sealed transaction protocol. And I hope we've done a pretty good job of explaining why we think this is a great way of doing things, and kind of demonstrating its flexibility and the fact that it incorporates a lot of best practices into a very understandable structure. So I'm open for questions.
Now, would you go back to the benefit slides?
Yeah.
So the key thing here that I want to point out is that this is the foundation for a wide variety of protocols. Obviously, our first use case is the Gordian depositories, but can really be used for a wide variety of other things. I'm hoping to use it with Git repos for supply chain security. It can be used in, a wide variety of protocol situations. And many of those protocols can many of the protocols can also take advantage of the general benefits of envelope, with in particular elision. So, we can have a situation where, I send you something, we establish a tofu, but then you decide, well, I'm only going to give you some information back because you have not fully authenticated. Here is how you can fully authenticate. And then, you basically can do a couple more rounds in there where you're slowly revealing additional information to each other to improve the trust that you have between the two parties. And maybe you don't even necessarily go all the way to the end of the protocol. You have sufficient information to be able to meet your risk model or whatever it is that's appropriate for you at that particular point. And although there might be additional steps that someone can go through, it is sufficient for you to take action based on the protocol and do the function that you've been requested to do. So I think there's a lot of opportunities to use state, to use elision, to use other things. I mean, even as an example, I've been trying to puzzle out, there could be, when you actually put when you create, say, an envelope inside a Git repo, it actually might have elided your private keys. And you go, well, that seems kind of stupid. That's why would I put my private keys into a public Git repo? But that would then allow you to, for instance, to prove that the key did exist and in your past, or allow you to do some different types of things. And because it's just a hash and a proof of existence, you can basically do integrity checks in a very stateless fashion. I think there are a lot of opportunities here. For advanced protocols that I don't really see, anything else that supports it with the level of ability to do privacy, to do progressive trust and other different types of techniques out there. So this really, I think, is a foundation for a huge number of opportunities.
Yeah, I would
Um,
point out that because the envelope itself is a hierarchical structure, and because if you elide a branch of that tree, you're leaving a hash in place that is a cryptographic commitment to everything that was in that branch. But you can reveal just the top level of that branch without revealing everything down inside it. But at each step, that when you reveal that, you've basically not just revealed that yes, you know what was in there that you were committed to, but also you can reveal just parts of it and leave the rest delighted too. So you haven't revealed everything yet, but you're still committed to what's there.
Also, we're taking advantage of a variety of in the same way I was talking about SSH demonstrating not necessarily cryptographic agility, but cryptographic flexibility. We have this same kind of flexibility in the future for how we do the permits. I mean, right now we have two ways to recover the symmetric key that lets you unwrap an envelope. We have the way that was demonstrated here with the sealed message with the ephemeral private key with ephemeral keys. But there's also the SSKR method where you basically, oh, I have to assemble things from multiple places. There could be additional ones in the future that, for instance, used Frost. Where it required a quorum of parties to basically agree in order to unwrap the next level of the envelope. So there's a lot of interesting capabilities there. Uh, Ken, did you want to just make a quick statement or anything? We thank you for your support for this research. Oh, he left. Okay. Again, we want to thank Foundation Devices for helping us get to this point, and all of our sponsors in the past that helped us build the foundation underneath this of envelope and SSKR and seeds, etc. We are at 4 minutes past when we should be ending. So, any last questions before we continue? And record this and save this